Welcome to a solo purple teaming supplemental lecture. We're going to jump into the concept of bypassing brittle detections. But first, a disclaimer. This lecture is intended solely for educational and authorized security testing purposes. Every demonstration, tool, and technique you'll see is presented to help you understand how real world adversaries operate so you can better detect, defend against, and respond to modern threats. By continuing with this course, you agree to use all information ethically and legally and to obtain proper authorization before conducting any red team, penetration testing, or security assessments. You are also responsible for complying with all applicable laws, regulations, and organizational policies in your environment. The instructors are not liable for any misuse of the material presented. Ultimately, how you apply this knowledge is your responsibility. Use it wisely, professionally, and with integrity. In this lecture, we'll examine brittle detections, what they are, why they exist, and why attackers routinely break them. Brittle detections rely on specific strings, patterns, or execution assumptions rather than behavior, which makes them effective in demos but fragile in real world scenarios. We'll start by reviewing how AMZ inspects script content at runtime, focusing on visible content rather than intent. Next, we'll examine how Windows Defender performs static inspection using signatures, heuristics, and known byte sequences before execution. With that foundation, we'll demonstrate bypassing both AMZ and Defender using simple techniques like string concatenation and base64 encoding, showing how minor variations can evade pattern-based controls without changing any of the behavior. The goal isn't to teach evasion, it's to expose the limits of pattern based detections and reinforce why resilient defenses must focus on behavior, not appearances. Many detections look strong on paper. They fire consistently in clean demos, dashboards turn green, and breach and attack simulation tools report success. On the surface, everything appears to be working exactly as intended. The problem is that these results often create false confidence. Clean demos and BAS tools usually test a single sanitized execution path. They validate that a detection can fire, not that it can survive variation. Execution order stays the same. Strings don't change. APIs aren't swapped. Payloads aren't transformed. Attackers don't operate this way. They introduce noise, make small adjustments, and adapt as soon as something fails. When detections are tied to specific procedures or tools instead of behaviors, they break the moment reality deviates from the script. This is why solo purple teaming focuses on realism. Instead of chasing individual tools or one off techniques, we analyze real malware to identify the least common denominator across malware families. That is, the behaviors that persist even when implementation details change. By building detections around these shared behaviors, we move away from brittle, signature driven logic and toward resilient detections that survive tradecraft evolution and hold up in real environments. Traditional antivirus relies heavily on signature based detection, looking for known byte sequences, hashes, or strings. This works well at scale, but breaks down with even minor variation, something that you'll see during the demo. Simple changes like encoding, reordering, or trivial obfuscation can alter a signature enough to evade detection. These systems are optimized for speed and coverage, not understanding the intent or behavior. As a result, antivirus can appear effective in controlled tests yet fail quietly in real world scenarios, revealing why signature based detection is inherently brittle. The anti malware scan interface, otherwise known as AMZ, gives security tools visibility into script-based execution. It inspects script content at runtime before execution, allowing it to analyze scripts that may never touch disk. AMSI is tightly integrated with PowerShell and other scripting engines, making it effective against common attacks. However, it can only evaluate the content it sees at inspection time. If no recognizable malicious pattern is present, execution is allowed. AMSI is effective when it's clear text visibility into a script. It scans readable PowerShell content and matches it against known strings and patterns. Its limitation is that it evaluates text, not intent or behavior. When clear text is disrupted through string concatenation, encoding, or runtime reconstruction, recognizable patterns never appear during inspection. The behavior doesn't change, but AMSI loses visibility, which is why AMSI-based detections are inherently brittle. Let's go ahead and see AMSI in action. I'm going to jump into the lab, and right here I have payload all the things open with the reverse shell cheat sheet page, and we're going to copy a PowerShell reverse shell payload here so that we can use it in PowerShell, and we're going to show how AMSI catches the payload. Now, this is a known payload, right? And so AMSI should detect this, right? And a lot of these AVs and signature-based detections are reactive, meaning the event has to have happened for a signature to get created, and therefore they're not proactive. So if I paste this in here, what we're going to get is the script contains malicious content and has been blocked by your antivirus. This is AMSI at work. Now, in the Solo Purple Teaming course, which we'll talk about later, I actually deep dive into how you can reverse engineer AMSI a little bit to understand how AMSI is doing this inspection. But for now, we'll keep it at a simple level, and we just know that AMSI is scanning our script before it executes to look for signatures to be able to determine if the script is malicious. Now I'm going to jump back in the slide for a little bit more theory, and then we'll actually bypass AMSI. One of the simplest ways to bypass AMSI is by breaking its visibility into readable strings. Techniques like string concatenation, variable reordering, and runtime assembly prevent recognizable patterns from existing at inspection time. The behavior never changes, only the representation does. The same actions occur, but AMSI never sees a clear text string to match, highlighting the inherent weakness of string-based inspection. Let's go ahead and jump back into the lab and see how some simple variations can bypass AMSI. All right, so we already saw that our payload's being blocked by AMSI here. And here's our payload. The first thing I want to do is convert it into more of a script instead of a one-liner. So I'm going to get rid of the beginning of this script. So let me do function left arrow so I can get to the beginning. And what I mean by that is this is a PowerShell command, right? We're using a -C option, and it's a bunch of commands strung together inside of a string using separated by semicolons. So I'm going to go ahead and get rid of those because I need to be able to see each command, and I'm going to run each command one at a time so that I can identify which one is being flagged by AMSI. So I'm going to break everywhere I see a semicolon, I'm going to break those onto their own line. All right, I'm gonna get rid of this last double quote and change that to a semicolon. Okay, perfect. Now we have them all on one line. What I can do is change this first line because I need to make an actual client. So I'm going to connect to a Kali box. So 10.1.0 I have a Kali box at 10.1.0.225, and we can use the same port. Now I'll jump over into Kali and start a listener on 4242 so that we can make that connection. We need that connection because we're going to run this command one command at a time so that we can go through all these commands and identify which one is causing AMSI to detect it. Now you can see defenders popping up left and right every time I make a change to this script because it obviously detects this as a malicious script. And we'll talk about Defender after we bypass AMSI. Of course, we'll be able to bypass both AMSI and Defender when we're done. So now that I have that, I'm going to jump into PowerShell. I'll go ahead and get some real estate back. Now I'm going to run this command. Now that command executed. In fact, I can see that if I type client, it's going to tell me that I have a valid system.net sockets.socket. So that has been created. Execution, no problem. AMSI didn't flag it. So now I'm going to go grab each command one at a time. And I'll kind of go through these quick if I can. That doesn't flag AMSI. AMSI didn't flag that. Now this while loop's a little bit different. Let me show you what we have to do here. So we're going to start the while loop. All right, so we pasted that in, hit enter. Notice we get these double carets here. That means PowerShell's waiting for more input because this is a while loop. Notice that it has a curly brace here. We need to close that curly brace. But before to do that, I'm going to grab one more command here that's inside the while loop so that we can execute another command. I'll paste that in, hit enter, then I'll close the curly brace and use a semicolon here, and we got execution. So these lines right here do not cause AMSI to flag any malicious behavior. So we'll continue. I need to kill this connection so I can rebuild it. I'll go ahead and hit up arrow and start my listener again. Now I'll go ahead and create my client again, create my stream again, grab the bytes object here, and we'll build our while loop. But this time we're going to add another line here. So I'm going to go here and add this line. Oops. I need to undo that. I just pasted over on accident. So copy that, paste that line in here, hit enter. Now we'll close our curly brace and semicolon because we need to execute the code so that AMSI will inspect it. So it inspects it right before execution. So I'll go ahead and hit enter, and now we see we get malicious payload. And the problem is I copied two lines on here. So let's break these lines up because there's multiple lines here on that same line. So I'm going to go through this process one more time. Let's go start our listener. So we got a client here. Let's create a stream. Bytes object. Our while loop. I want to break this up because there's two commands here. Oh, here's a better way to do this. I'm going to just get rid of this command here. Let's run it this time like this. And notice that it runs. So we know that this is where the AMSI is detecting the malicious script. So let's go ahead and verify that. I'm going to go ahead and kill this connection one more time. Hit an up arrow, start the listener again. And let's go back into PowerShell. And we're going to go through the whole process again. Create the client, create the stream, get our bytes object, Let's do our while loop. So this was the last loop, but let's go ahead and hit back. And let's change this up a little bit, right? So we know we need to change this line up. I'm going to go ahead and hit enter here. And notice Defender continues to go crazy because it does see this as malicious. Now, what this does right here is create the prompt here. So what we want to do is modify that somehow. Now, I personally don't think you need the present working directory, but you could manipulate this if you wanted to keep this prompt the same way. But in the short run, just to prove that we can bypass AMSI with a simple change here, I'm just going to get rid of the prompt. And it's just going to give me a caret instead of PS working directory and caret. Now, the working directory is nice. If you want to work towards that, you can definitely obfuscate it. Just use some concatenation or something like that. And you will be able to get the prompt exactly how you want it. But I'm save this right here. Nope. Control A, Control copy. Now I'm going to run this and see if we can get a working shell. Let's go ahead and close this connection and start my listener. We'll go back into PowerShell. Um, I'm just going to paste that whole script in. And I'll hit paste anyway. It's going to run that whole script that we ran. Now I jump back over here. We have our connection. I hit enter. Notice how our prompt changed. So this is not what it normally looks like. It's just a simple prompt, but we do have the prompt and it does work. So I just typed the dir command and it showed me all of the listing. So it showed me the directory listing. So we have a valid shell, a working shell. And all it took was small variations to bypass AMSI. Now that's great, but I need this to be a one-liner. So I'm going to go ahead and close this connection here. And we're going to make this a one-liner. So back to how it was before. So I'm going to put all these back on one line. Maybe. And I'm going to turn this back into a PowerShell command. So PowerShell dash not dash C double quote, and we need to go to the end of the line and put a double quote. So this should allow us to run this as just a single one-liner. So I'm going to go ahead and copy it and jump back into PowerShell and see what happens. Oh, let's go have PowerShell open twice. Did I close it? Yep. Make the font a little bit bigger, and we can make the terminal bigger. And I'll paste that in, right? Here's the PowerShell command. And notice that AMSI's not catching it, but Defender is. So let me go ahead and start a listener. Uh, so Windows Defender is now catching it. And this gets access denied because Defender catches it. So we've bypassed AMC. Now we need to get this one-liner past Defender. Did we get a connect? Nope. All right. So the next thing we want to talk about is what failed, right? AMSI failed in this case because the detection was content based. It evaluated the script text it was shown and attempted to match it against known strings and patterns. When we changed that one string for the prompt, we were able to bypass the signature that AMSI is using to detect that reverse shell. Importantly, the behavior remained unchanged. We still ended up with a working reverse TCP shell where we could execute commands remotely. The detection also assumed a fixed structure, expected strings to appear in a predictable order and format. Once that assumption was broken, the detection collapsed. This is the core limitation of AMSI-based string-dependent logic. It can only detect what it can see, and it cannot reason about the behavior that emerges dynamically at runtime. Now, Windows Defender, which is now detecting our payload, relies heavily on static file scanning, analyzing on-disk content for known signatures, patterns, and structural indicators before execution. It also uses cloud-based machine learning to quickly identify known or suspicious threats at scale. However, Defender has limited visibility into runtime behavior and memory-only execution. When code is decoded or assembled after execution begins, it may evade static inspection, highlighting a key limitation we'll build on next. Plain payloads get flagged because they contain known byte sequences or recognizable stagers and predictable structure. Their raw bytes, readable strings, and common execution patterns closely match samples antivirus engines have already seen. With no ambiguity to resolve, detection is fast and reliable. This is why unmodified payloads are blocked so consistently, and why even small changes can dramatically alter detection. Let's jump back in the lab and see if we can bypass Windows Defender. Now, what I think we could do is just use some type of encoding to encode our payload and avoid this detection by Defender. So I'm going to go ahead and jump back to my payload here, and I'm going to go ahead and copy it. So Control A, Control C, and I'll jump back in here and clear to get some real estate back in the terminal. Now I'm going to create a variable called C, and I'm going to paste in my payload. So I'll just right click and paste that in. Now I need to modify this. One is when you use double quotes, PowerShell will interpolate variables, and I don't want that. What I want to do is those variables will be treated as literal strings. So I need to go back first. I'm going to hit FN left arrow. I need to get rid of this PowerShell-not-C because we want a string, not a command here. So I'll go ahead and get rid of that. So C equals. Now I want to change this first double quote to a single quote. Notice how this changed the color of those variables to blue. So those are treated as literal strings. And I need to change where I was using single quotes to double quotes. Or I could have escaped them. Now notice that we're pretty close here, but we have one problem. We have double quotes around the greater than symbol, which I'm trying to get to here in a second, which will change those to double quotes. So right here around where we're building our prompt, we use single quotes, and we need to change these to double quotes. So they're A inside the single quotes. And then at the end, I need to get rid of this double quote and change it to a single quote. So this will create my string. Now I can just print C, and you can see it's our payload. Perfect. Now I'm going to take this string and convert it to base 64. So I'm going to use system dot convert, and we're going to convert to base 64 string. And this takes a bytes object. So we need to pass in bytes to base 64 string. So we need to convert our string to bytes. To do that, we use system.text.encoding Unicode dot, and we're going to get bytes. And we'll pass in C, and we'll close our convert to base 64 or to base 64 string call. So hit enter. Oh, I have a problem here. What did I do wrong? Oh, I didn't put C here. I didn't use my variable. So let's clean this up. This is a little typo. This is my variable name. Now we get our base 64. So this is our base 64 code. I'll copy this. And now let's make sure our listener is running. So log back into my Kali box here. And we have our listener running. So let's go ahead and use PowerShell to execute this encoded command. So I'll use -E, paste in my base 64, hit enter, and voila, connection. We are now bypassing both AMSI and Windows Defender. And we have a one-liner that we can use in a payload. So with that said, base 64 works because it hides content from static inspection. Encoding removes recognizable strings and byte sequences from disks, leaving scanners with unreadable data. It also delays visibility until runtime. The real content only appears after decoding, once static inspection has already finished. The behavior doesn't change, only the representation and timing do, making base 64 effective against signature-based detection by moving malicious logic outside the static inspection window. Success. So we've walked through kind of what brittle detections are. We're able to demonstrate how AMSI is signature-based and it's brittle, so it's pretty trivial to bypass. We didn't use any type of AMSI patching or any type of kernel exploits. We just made minor variations. And we also bypassed Defender, just making a minor variation by using base 64 encoding. If this approach resonates with you, if you care about detections that survive real attackers and not just clean demos, then you'll feel right at home in Solo Purple Teaming. The course is built around realism. We analyze real malware, break down how attacks actually work, and use the understanding to design emulations and detections that hold up when tradecraft changes. This isn't about tools or checklists. It's about learning how attackers think, how detections fail, and how to build coverage that lasts. If you're interested in going deeper, you can find Solo Purple Teaming on Udemy, and there's a coupon code linked in the description to get you started. That's all I have for you. I thank you for watching, and please, if you like this content, subscribe and hit the thumbs up.